All right, line R1, we're in learning task number 3. We're taking a look at HID lamps at this point, and what we classify as being our general types of HID lamps. We have already looked at fluorescent lamps and the low-pressure sodium lamps, which are a type of gas discharge. However, those ones are going to be a low-pressure type. What we are going to have right now is we are going to be going through our main types of lamps that are going to go and be high-pressure and short arc form. If you compare a fluorescent tubes, anywhere from as short as 6 inches on those really small ones, all the way out to 8 feet long. They can have a ridiculously long arc tube, and we're going to have, neon or argon or krypton or something like that we will use to go and strike that arc across there. And so we carry it, we ionize it, and then we create that UV radiation changing into visible light. These ones are going to be bulbs that, although large, are going to go and contain a relatively short component that we are going to go and refer to as the arc tube. And that arc tube is going to be operating at a way higher amount of pressure and temperature than what we would have had inside of our fluorescents. So let's go through these. We're going to start with the very first one that we have, which is going to be our Merc Vape. The Merc Vape is an old type of lamp. We no longer put these ones in. Obviously, the predominant material used in its manufacture was going to go and be mercury. Not so much of a safe material to go and utilize. But we'll go and explain kind of what's happening inside of the Merc Vape because it was our earliest one and everything else has been kind of built from that as far as our metal halide goes. Inside of the Merc Vape, we have got the quartz arc tube. Quartz being a type of element that's going to be relatively high temperature. It's a really hard, strong, clear type of material over there. Inside of there, we are going to go and have 3 probes. This probe, and this probe over here. 2 of them are going to be operating electrodes. One of them is going to go and be a starting electrode. So what we need to do in order to establish current flow is we need to start by getting to a high amount of heat, and we have to start with some ionized air that's carrying current. So inside of here, what we have, if you take a look, we've only got 2 leads, right? We are going to go and have the base contact. We're going to go and have the screw shell contact over here. But what we're going to be able to do is we're going to establish a small amount of voltage difference just through induction and through this resistor that's going to be placed inside of there. They rate this thing as being a long life resistor. What happens is they go and run current up through here. This long life resistor is also going to go and have a very small contact point that goes across the other line. That's going to be a bimetallic, and it's going to go and bend out of the way. So what we have is initially there's going to be voltage placed across these 2. That's going to go and establish a little tiny arc over there across that starting electrode. As soon as we get current flowing through there, that long life resistor included with that bimetallic strip over there is going to go and open that circuit. But at that point, what we have done is we have already created that ionized air pathway, which means that now we are going to be able to jump that ionized air pathway across to there. So this one cuts out, but because we're already at an operating temperature, this one over here is going to go and jump across. And so then we have a continuous arc that is going to be burning inside of this tube over here. We have got a mercury gas mixture that's going to be inside of there, and it's going to go and take a couple of minutes to come up to full temperature and to come up to full brightness. Basically, what we're waiting for is we're waiting for more evaporation of the mercury to happen inside of there. And as the mercury evaporates, every time it breaks down to smaller chunks, that means that we've got more chunks that we can strike with electrons inside of there, which means that we can get more emission of light itself. It does take a fair bit of time to go and come up to full brightness. And if we accidentally shut these things off, it is also going to go and take a fair bit of time to go and restrike. Restrike just means a hot bulb, restarting once again. This one doesn't have a greatly increased amount of restrike time compared to its initial startup time that we had. So it's not a huge deal when these ones go out. It's not a lot different, than starting them the first time. But it's still a little bit of a wait. What we're waiting for is we're waiting for this tube to go and cool down and for this thing to drop to a lower pressure, right? Heat causes pressure. Once we get to that lower pressure, then we're going to be able to go and restart this thing. They do have very good efficacy. Not as high as a lot of our LEDs, but they were a great efficacy years ago, far better than what our incandescents were, and so we use them for a lot of our outdoor types of lighting. They did also have an extremely long lifespan, 24,000 hours, And they did also burn really well in our vertical position, which made them really great for inside of high bay types of lighting. Not so much for the arm type of lights that we would use in street lights, but in stuff where we could go and flip this whole thing end over end and just hang the bulb straight down. That arc wants to go always travel upwards. So we can, help that by actually operating this thing in an upwards direction. If we do have low ambience, they did have to go and have a special ballast, same as what our fluorescents, cold weather ballast that's going to give them a slightly increased starting voltage just so that they can initially get that ionization. But once they would be operating, they would be the same thing. We didn't have to have special lamps for the low temperature. It was just a low temperature ballast that was necessary for them. They do have a white light as well. So anytime you're looking at HID lighting that's got that kind of clear bluish type of white light, you're looking at either a mercury vapor or you're looking probably more likely at a metal halide, which is the one that was developed off of these ones. Let's go and switch over to the next one, which is going to be our metal halide. Metal halide is going to be an improved one of these. Oh, actually, I got to go back and just mention something. These things will continue to burn if you lose this outer glass envelope. If the rest of the guts of this stay together, but you would lose the outer glass envelope or you'd have a crack inside of it, you would continue to go and get light output. However, you are also going to go put yourself in danger because the outer glass envelope does contain a small amount of embedded phosphors and coatings on the inside, and that's what changes the UV radiation that's generated inside of the quartz arc tube. Quartz arc tube also being phosphor coated. That is what changes it to visible light. So if you've got a crack, you're going to just be leaking UV radiation, which isn't good for anybody. Generally speaking, anything that's cracked and broken should be taken out of service. I mean, this is just one of the things that's mandated inside of our electrical code, but there's danger if you do leave these things operating. Metal halide, that was the one that we said was developed off of it. Very much the same thing. It has got an arc tube that is going to be a slight bit smaller inside of there, but the same sort of setup. We've got, once again, 2 contact points. We're going to have the base. We're going to go and have the screw shell. That's going to be my 2 lines in. We are going to go and have a starting electrode, as well as we are going to go and have my main operating electrodes that I'm going to have as well. And we're going to do the same thing where we're going to strike a small arc over there. Once we get that little arc rolling, then we are going to go and send it across to the other main electrode. At that point, the starting electrode shuts off, and we continue to go and burn inside of here. We have that passage of currents. The current is going to go and strike small amounts of mercury. We have not gotten completely away from mercury. There's still a small amount inside of it. But they've also got some sodiums and some other metallics that are going to be inside of it. So it's just less dangerous, not that it's completely danger-free at this point. They are also going to be that same bluish, whitish light that we're going to get out of them, and a large amount of light. Once again, these are things that we're commonly going to see inside of high bay lighting, and we are also going to see these things inside of a lot of street lighting, those really whitish street lights that we have. It is going to require a higher starting voltage because we're using less mercury. It's harder for us to go and get this thing started and to continue running it. So we compensate for that by going to higher amounts of voltage and by shortening that gap distance that we have. From end to end over here, we're going to bring that thing down a little closer inside of here. Because it's a smaller tube, that means when we get that arc going inside there, we're also going to go and build to a higher amount of pressure. And that larger amount of pressure means that these things are going to have a much, much longer restrike time. Generally speaking, turning them on is about a 5-minute process. You turn them on, you hear the boom, and then they kind of start flickering, and then they start coming up to full light output, and then you're going to be fine. But as soon as you would go and shut these things off, they need to cool sufficiently before we are going to be able to go and restart them. What we're actually waiting to go and happen inside of there is, once again, these things that they keep identifying here as long life resistors. They're going to be incorporating some bimetallics that are going to open those circuits up. All of that needs to cool down inside of these super high temperature bulbs. Both of these, well, actually not just both, but all 3 of these HID lights that we're talking about are ridiculously high temperature. You never touch one of these things when they're burning or when they have just burned. You got to wait a little bit for these things to go and cool down because they just operate at insanely high values. All of our fluorescent lights, you can touch a fluorescent bulb all day long. You're not going to get burnt off of that thing. Same with those low pressure sodiums, which are a form of fluorescent. You can also, come in direct skin contact with them. But these are very, very dangerous to come into direct skin contact. There are special ones of these type, the metal halide, that can be used inside of some of our other types of fixtures. So a metal halide is kind of more or less our universal one we can use, and not just any one, but specially rated ones. You can use specially rated ones of these inside of both your merc vape, as well as you're able to go and use some of them inside of your high pressure sodium fixtures as well. They do all have the same type of, base that's going to be that mobile or that very large type of screw shell base. So you could just take out, what you had for your previous bulb, replace one of these. But once again, just make sure that it is one that's suitable to go and replace. It would say, suitable to replace a 400 watt, high pressure sodium and maybe a 250 watt metal mercury vapor or something like that. You just want to make sure that they are going to be compatible. But if you do have any that are going to be crossovers, it will be these. It's handy because you don't want to necessarily have to go and change the ballast or the entire fixture. But, when it comes to a mercury bulb, you're not going to be able to necessarily find one of those as well. The efficacy is going to be higher than our mercury one. So we do get better lumens produced for the watts, but we do sacrifice a little bit of our lifespan. Generally speaking, operating something a little bit lower leads to a longer lifespan, and so the mercury vapor would last longer. These ones have got about a 3/4-ish the lifespan, and we're sitting around that 15 to 16,000 hours that we are going to have inside of them. And we do have another type of lamp as well that's going to be a pulse started one inside of here that does not contain the same starting electrode. What it does is it has a really, really high voltage, like a DC ignition coil, that is going to go and pulse, and it'll actually drive that across from here to here. Because of that pulse start technology, you cannot utilize a pulse start bulb inside of a regular high pressure, or inside of a regular metal halide lamp, because it doesn't have that starting electrode, and therefore you would never be able to initialize that arc. It's not going to ruin anything, it's just going to sit there wanting to go and strike, and it's impossible for it to do so. Your pulse start lamps, because of that lack of electrode, cannot be used inside of a regular metal halide fixture. A regular metal halide bulb, however, can sometimes be used inside of your pulse start ones. It just means that it's not utilizing. This would just become kind of an extra appendage that it no longer needs. It's kind of like the, I was going to say kidney, but that's the wrong thing. There's another little organ in there that people sometimes lose. Oh, whatever. I cannot remember those things because that's not my area of expertise. Appendix. That's the one. Sorry, appendix. It was just going to bother me too much if I didn't remember. It's kind of like the appendix at that point. It's not necessary and can be, lost if need be. All of these bulbs that we've looked at as well, I did warn about that, danger of skin contact for the high temperature and for burns. The other thing that I want to iterate with these things is that bare skin contact, even when cold, is not recommended, because anytime that you touch, you are going to go and leave greasy old skin oils. You've got, when you're working, you've got a lot of buildup in all those little, skin cracks on your hands and stuff like that of just random contaminants and dirt, but it's those oils on there that would not go and evaporate, and they would lead to uneven heating on the bulbs. And what happens with that uneven heating is then we start to develop small hairline cracks. So wherever you've got fingerprints on these bulbs, that's where you're going to go and get uneven heating, because now you've got that positive oil that's sitting on there, and then it's going to start to crack out at that point. So whenever you're putting these in, use gloves. You should have a pair of good, clean cotton gloves. If you're doing a lot of this work, you just keep a little pair inside of your jacket pocket, but you want to try and keep oils off of these things. All right. The last one that we have over here is going to be my high pressure sodium. These ones are going to be a yellowish light, not nearly to the same color as what we had off of that low pressure sodium, but once again, we're looking at a large amount of sodium that's going to be inside of here, and sodium burns yellow for us. So we are going to get that same yellowish whitish, but it's got a better CRI, high enough that we can actually start to go and classify it as a CRI. I don't know if you remember that about the low pressure sodium, but we couldn't even classify the color rendering index. These ones do have proper CRI. They do not have a starting electrode, and inside of their bulb, they have got a ridiculously long ceramic discharge tube. So it's going to be made out of a, not clear, but it's going to be made out of like an opaque, translucent, not opaque, but translucent polycrystalline alumina that they have inside of there, which is a hard substance, and it's once again going to be a high temperature. substance. And then inside of that, they've got a little bit of a neon, that's the xenon gas, and then they've got a little bit of sodium and mercury amalgam inside of there. The mercury inside there starts to pull it away from being all the way in the yellowish spectrum. The sodium that's inside there does give it that little bit of yellowish spectrum. So, we kind of counterbalance them. What we have to do inside of these is we need to strike a high arc off of these. That high arc is going to go and travel the length of the tube, ionizing the gases inside, and then, starting out this whole gas discharge thing. Once again, collisions between electrons and the tiny amount of mercury and sodium in here, that's then going to start to create our UV, which we can then change into our visible light. Sometimes the outer glass envelope is going to be coated, like it's going to have a phosphor coater. Other times it's going to be clear inside there. It really depends upon the color that you're trying to shift it to. Generally speaking, the phosphors, they're trying to shift it away from that yellowish towards more of a bluish type of light. And so they'll just use the color shifting properties of phosphor to be able to do that. They do have that ridiculously high amount of voltage to go and establish this arc. This tube inside of here is usually going to be about 6-8 inches across. So we're going to have to be up to thousands of volts across there. Because of that, you must be careful with these things when it comes to actually working on them. Most of the other ones operate at higher voltages, but they don't have these high impulse transients that we are going to utilize in the same way. Be careful around these ones. They do have a fast light. They're going to be about 3 to 5-ish minutes or something like that for them to come up to full brilliance. But it's not a super long time. And when they do have a restrike, the restrike happens relatively rapidly. Not as rapid as the low-pressure sodium, but, we're looking at about a minute. They do not care as much about the amount of heat as what all of our metal halide and our merc vapor are going to go and have. They also have got the highest efficacy of all of our HID sources. So we're looking at the best conversion of watts, electrical energy, to actual lights, lumens that we are going to be able to send out to surface. They do have a long lifespan as well. That's going to be very similar to what we used to get out of the old Merc vapes here, about a 25,000 hour of burn time that we can go and have. And they have been widely used. Anytime it's that yellowish light, you're usually looking at a high pressure sodium. Once again, careful with these things. If you are touching them, they are going to be hot. They do have this outer envelope that they are going to go and have. That's this over here. And they're going to try and pull out whatever heat they can out of here. But there's still going to be radiation, heat radiation that happens through there that is going to go and make this envelope really, really hot. So be careful, and once again, use your gloves. Remember as well that if you have one of these that is not working or that is broken, they have got that high open circuit voltage, that striking voltage, so just be very careful with these things. All right, the next section starts talking about bulb shapes. They talk a little bit as well about the interchangeability of lamps. We talked about that when we were looking at our metal halide, that our metal halide are the ones that can sometimes replace both the high pressure sodium and the mercury vapor, but it's once again not every single bulb out there. You need to make sure it is a properly rated bulb. Over here we have got a classification of lamp styles that we are going to go and have. We've got bullet, bulge tubular, elliptical, parabolic, aluminized reflectors. We call those PAR lamps. And then tubular, they're showing us just really the elliptical and the bulge tubular because those are the most common shapes that we are going to have. It is very common to go and have this squaring off of the ends because we need to go and have a way to support this. What we're going to have is we're going to have spring dome supports that are going to go and support the inner arc tube. So usually there's just a little piece of metal up top here. It doesn't conduct anything, but it's metal, so it's not going to melt. And then we're going to go and clamp it inside of the bulb. And us having that straight wall side over there allows this thing to stay centered so that the bulb is not going to get destroyed by vibration. So it's a very common thing. Anytime that you see this, that usually means that there is an internal support at either end of the bulb that's holding something in place if we've got straight sides to our lamps. Codes. What do we have to talk about codes? Yeah, they talk a little bit about the different coding that we're going to have. You should be familiar with the BD versus the BU. That's a DBU. BD is going to be base down. BU is going to be base up. They're talking about this over here. Some of them have got only certain positions that they're able to go and burn in. Other ones are going to be termed as being just a U for universal. Can be, you know, base up, base down, can be sideways or anything like that. And then on the bulbs themselves, we're going to go and have, once again, a number of different things that are going to be laying out the information. So we'll just write out the one that they have here inside the book. They've got an H. The first letter is going to go and indicate what type of lamp we're looking at. H is going to be for mercury. It's a chemical Hg that we have. M or MH is going to be for metal halide, and S for high pressure sodium. So know those ones that you're going to have. Then you're going to go and have a ballast type. We have got a universal number of ballasts based upon these different bulbs. You know, the manufacturers said it's easier for us to build bulbs to, you know, a set number of ballasts than it is for us to have to go and build a whole pile of different ballasts, you know, to match these bulbs. They just adjust their spacing inside of the lamps really to, you know, match the ballast type. So we've got all these ANSI types of ballasts. These ballast numbers are going to be stamped on the actual ballast. If you're not sure if it's going to go and work with that, you check the bulb, and if the ballast has got a 36 and the bulb has got a 36, you're going to be good to go with it. Just because there's an existing bulb in there does not mean it's the only bulb. That's the beautiful thing about ballasted lighting, is a lot of our ballasts can go and run multiple different types of lights. You just have to make sure that they're once again going to be compatible. After that, they give us just a designation for what this is going to be, you know, my shape, bulbs tubular over here. Sometimes this does make a difference. If I take a look at my ellipticals, you can see that my ellipticals obviously are going to be much narrower than my bulbs tubulars. My bulbs tubulars will not fit into all of the same lamp fixtures as my ellipticals. Same with my ellipticals, which are going to be a longer end-to-end, will not always fit inside of my bulbs tubulars. That being said, looking at these two classes that we have over here, this side over here is mostly going to be my high pressure sodium that we are going to go and have. This side over here is mostly going to be my metal halide bulbs that I'm going to have. And at this point as well, I should point out that we do have LED bulbs that we can go and direct replace into a lot of these fixtures. Some of them still utilize the ballast. Other ones are going to ask us to, you know, remove the ballast out of there. The last section is going to be the wattage. So if we've got a 1000 over here, that's going to be 1000 watt that this is going to be dissipated by the lamp. That's going to be the number of watts that are going to be generated as heat as well as by lumens, right? Based upon what the efficacy is. If I've got a 63% efficacy for my lamp, then that would mean that my lamp would have 630 watts that would convert to light, and the remainder, that's going to be, you know, 370, would be heat coming off of that bulb envelope. This is also just limited to the bulb itself. There are going to be additional losses that you are going to go and have inside of the actual ballast part of it. And then the last part that they have over there is going to be DX. This is going to be color coding. It is not always on every bulb that's out there. Sometimes you'll see it on there. DX is just going to be a deluxe phosphor coat that we're going to have, or it's a white one, and then we could get the WDX, which is going to be a warm one. Once again, the colors, you know, warm and cool, are also going to be designated by kelvins. And you should know this as well anytime that you're looking at bulbs. It's just what your different kelvins themselves mean. 3000 kelvins. We'll start all the way down here. 2700 kelvins. And then we'll go all the way up over here. We'll take this thing to 5000 kelvins. Kelvins are going to go and be degrees. Not temperature degrees the way that we look at them when it comes to light, but it's going to go and talk about the degrees of warmness that we're going to be using. 2700 kelvins is what we would go and term as being our warm colors. And anything that's, you know, 5000 Kelvin would be what we would term as being a really cool color. Those are going to be the bluish white types of colors. And these other ones are going to be, you know, the really yellowish, you know, warm is the best way to, you know, describe it. They do cause humans to respond differently. Warm lights do tend to relax humans. This is what you should have like inside of your bedrooms and things like that. You've probably done like the color shift on your phone or on screens before, where you can make it shift to, you know, warmer color tone when it's going to be getting later at night, because these cool color tones over here cause more alertness. They're much more like a springtime type of bright color. So we'll often see cool colors that we're going to go and utilize in areas where we want to go and have high production. Offices, you know, warehousing, things like that. Obviously, we want our workers to be working, so we prefer to have those cool ones that tend to keep them a little bit more alert. And then if we would have anything that's designed to go and be like a relaxing type of space, or an architectural type of space that's supposed to be inviting, will oftentimes have warm colors inside there. You should get good at recognizing these as well. There's nothing that drives, a good electrician nuts more than seeing that, 4-foot fluorescent fixture that has got 3 tubes that are going to be warm, and then that 1 cool tube that's inside of there. You just don't be screwing around with that stuff. Keep the same color temperatures and just get used to reading them and replacing them like, a real professional would. All right, that covers off our lights. We're going to go and talk about the ballast next.